Well, good morning. I welcome you to this session of basic thermodynamics. So, what we are discussing last class is the thermodynamic equilibrium of a system. Just to again repeat it, that for a system to be in thermodynamic equilibrium, the properties should remain invariant with time and that should be uniform. The properties should be uniform within the system. So, this can be done by two ways, either by allowing the system boundary to be such that system cannot interact with the surrounding. Another way of doing it, another way of obtaining this, that when the system properties are same as those of surroundings, that means there is no imbalance between the properties of this system and the surrounding. So, in this regard, there are to meet this thermodynamic equilibrium of a system, three types of equilibrium are necessary. These are like this. If we write thermodynamic equilibrium, okay, if you write thermodynamic equilibrium, it has got one is three types of equilibrium are needed. One is thermal equilibrium, another is mechanical equilibrium, another is chemical equilibrium. These three equilibrium have to be maintained simultaneously to have thermodynamic equilibrium. Let us first discuss on thermal equilibrium. Now, regarding thermal equilibrium, there are three issues which come into picture. One is thermal equilibrium itself. If we write the thermal equilibrium, what is thermal equilibrium? In this context, one very important law of classical thermodynamics is the Zeroth's law. Then the concept of temperature. Now, it is the thermal equilibrium and the Zeroth's law which defines the temperature. Today, we know, it is very simple. Today we know the concept of temperature. What is temperature? If I ask you today, that you can tell there are two ways of defining temperature. One is the microscopic way of defining. It is the average kinetic energy of the molecules that gives rise to the temperature of a body. And this kinetic energy mostly composed of the translational kinetic energy. But if we define temperature from the classical physics point of view or classical thermodynamics point of view, today we know the definition is very simple. It is a property of the system. By virtue of the difference of this property, heat flows from one system to other. Heat flows from higher temperature to lower temperature, system of higher temperature to a system of lower temperature. So, this is the definition of temperature, which we can sense, we can measure, and it is a property, and the difference of which is responsible for heat to flow. Again, we define heat as that form of energy which flows because of a temperature difference from one system to other. What is thermal equilibrium? Now, this is also very simple. We know, we have read it earlier also. Thermal equilibrium is the equilibrium relating to the flow of heat. That means, if the two bodies are in contact, so that heat can flow between these two. So, thermal equilibrium can only be achieved if their temperatures are equal. That means, no heat will flow. So, thermal equilibrium means the equilibrium of temperature. So, all these things are known today. Of course, Zeroth law is a different way of expressing these two, but we now discuss how these things originated in the classical physics at the beginning. Though we know this thing, there is nothing new, that what is temperature we know. Thermal equilibrium means the two systems have to be at the same temperature, so that they are in thermal equilibrium, no heat will flow. But how this concept originated, let us discuss that, the concept of thermal equilibrium, and from which the Zeroth's law evolved, and finally we arrived at a definition of temperature in classical thermodynamics, the same definition, how it was arrived. So, that is why we will first discuss the concept of thermal equilibrium, the way it originated in the classical physics. This is important in studying thermodynamics, to discuss this. Let us consider this way two systems. One is system A. Let us consider this as system A, and let us consider this system is such that it can be characterized by two independent intensive properties. That means a single component, single phase system, XA and YA. And let us have another system which can be defined by any two such independent properties to define its states, that is XB and YB. And let us connect these two systems by a by an adiabatic wall. What is adiabatic wall? You know what is adiabatic wall? What is that? No heat can flow. So all the terminologies are known today, but it is true that this is known today, but the way it originated in the classical physics, I will describe that adiabatic wall. What is an adiabatic wall? The adiabatic wall is a wall which will be sufficiently strong to resist any stress developed because of the imbalance of the properties between system A and system B, and it is a kind of wall in practice made of wood, felt, asbestos, because originally it was conceived like that. The experiments were done like that. Then people came into the definition of adiabatic process, what is adiabaticness, what is diabaticness, all these things come afterwards. So initially it originated that let us have a boundary of that sort, wood, felt, asbestos, which does not allow the heat to flow, and it is sufficiently strong to withstand the stresses developed because of the imbalance of the properties. This type of wall is adiabatic wall. If you separate them by adiabatic wall, it has been found that now if entire thing is isolated from the surrounding, then it has been found, observe that a number of combinations of XAYA and XBYB are available. That means system A can assume any pairs of XAYA or any arbitrary values of XAYA. Similarly, any arbitrary values of XBYB for system B, they can assume any properties. So any values of XAYA and XBYB are available if they are separated by an adiabatic wall. Now if the same two systems, now if I same two systems, system A with the same XAYA and the system B, well, system B with XB, YB, they are available and they are now separated by a metallic wall which are good conductor of heat, for example. That is known as diathermic wall, diathermic wall, diathermic wall. And if they are insulated from the surroundings, then it has been found that some process will take place by virtue of which XAY and XBY will change, and the equilibrium will be attained by the two systems only certain restricted values of XAYA and XBYB. That means we cannot have arbitrarily all possible values of XAYA, XBYB like this. So some restricted values of XAYA and XBYB will be possible, so that no further change will take place between the two systems if they are separated by a diathermic wall. This is the classical concept of thermal equilibrium. So that means this gives rise to the definition of thermal equilibrium. Then the definition of thermal equilibrium comes in this way. Well, I show you. This gives rise to the definition of thermal equilibrium, which can be written now this way. This is the original definition in the classical physics or thermodynamics, that thermal equilibrium, the equilibrium states with this as concept achieved by two or more systems characterized by restricted values of the thermodynamic properties of the systems after they have been in communication with each other through a diathermic wall. So this is an equilibrium state of a system between the systems which they achieve with restricted values of thermodynamic coordinates when they are in contact by a diathermic wall. That means all arbitrary values are not possible. That is the concept of thermal equilibrium. All right. Now, if we go little further, then what we will see, now this experiment was made like this, that if there are two systems, system A with similarly XA, YA properties, well, system B with properties XB, YB, if they are now separated by an adiabatic wall, this is an adiabatic wall. Now, if we conceive a separate system C, let us consider a system C, with properties designated by XC, YC. All these systems are conceived for simplicity in understanding that they are specified by two independent properties, and if they are separated, that means system A and B are in communication with system C through diathermic wall. That means this wall is diathermic. Already I have shown by this color, diathermic wall, while this is adiabatic wall and everything is insulated. That means if system A or B in communication by an adiabatic wall and system A and B with C are in communication with diathermic wall, then what happens that XA-YA and XB-YB suffer changes as XC-YC change. That means this properties change XC-YC because of the interaction with system A and system B, and system A and system B the properties also change and they attain some restricted values. For example, at some equilibrium state we get some properties XA-YA, some property values XB-YB for system B and XC-YC for system C. Now, if we remove this and put these two systems after achieving this equilibrium, system A and system B by a diathermic wall, then we will see that by a diathermic wall, then what we will see that the system property, that means the property XA-YA and XB-YB won't change. That means when they are in thermal equilibrium what I will not use here, that means when they come to equilibrium with system C by a diathermic wall, both system A and system B individually, separately and individually, then their properties will come to a uniform and invariant values. Then if they are in communication with each other by a diathermic wall, their system does not change. This gives rise to the definition of zeroth law. This is simply, this phenomena is known as zeroth law of thermodynamics, which is very important in classical thermodynamics, which gives the definition of temperature. What is zeroth law? When two bodies or systems are in thermal equilibrium with a third one, then they are in thermal equilibrium with each other. Today this is very known fact. If you tell this to school boys at class 7-8 level, then they will tell this is known fact. But this is the way how it originated in the classical physics. So we have to go through this origin. So this is the basically Zeroth's law, and these two concepts of these two things, that the thermal equilibrium and Zeroth's law, gives rise to the definition of temperature in classical thermodynamics. If one asks you what is the definition of temperature in classical thermodynamics, how do you define? The temperature has to be defined without the definition of heat, without going to the molecular level, that it is not the average kinetic energy of the molecules. Then how do you define it? That is given by the classical thermodynamics. This is the definition. Because afterwards we will define heat with the help of the temperature as the property. So therefore, without taking the concept of heat or without consideration of the molecular events, we define temperature by Zeroth's law in classical thermodynamics like this. It is a thermodynamic property that determines whether or not a system is in thermal equilibrium with other systems. Well, so this is in short the concept of the thermal equilibrium. Now we come back to this thing, that a system to be in equilibrium, thermodynamic equilibrium, it has to fulfill the three equilibriums: thermal equilibrium, the mechanical equilibrium and chemical equilibrium. So thermal equilibrium we have now understood, that is the equilibrium of temperature. That means when the temperature is same between two bodies, there will be thermal equilibrium. What is mechanical equilibrium? Mechanical equilibrium is the equilibrium with respect to work transfer between the system and the surrounding. That means when there will be no imbalance of properties, any properties that will cause work transfer. For example, mechanical work transfer, there has to be an imbalance in the pressure between the system and the surrounding. So in terms of one of the primitive properties, pressure, we can tell, sometimes many books tell like that, that if there is no imbalance between the pressure of the system and the surrounding, the system attains a mechanical equilibrium. So mechanical equilibrium in a broader aspect is the equilibrium when system does not go with any process involving work transfer. But in a limited sense, we can tell is a mechanical work transfer. This is only responsible if there is the disbalance of pressure between the system and the surrounding. So there is no disbalance of pressure between the system and the surrounding, then there is no question of mechanical disequilibrium. That means the system is in mechanical equilibrium. Another is the chemical equilibrium. So chemical equilibrium of this system. Now you see, all this non-equilibrium is responsible for change of certain class of properties. When there is no thermal equilibrium, temperature, the property temperature goes on changing. Equilibrium criteria is that all properties should be invariant with time. Similarly, for mechanical disequilibrium, some properties will change, pressure will change, volume will change, some other associated properties also will change. This is sensed basically through the change in these properties. Automatically other properties will change because they are related depending upon the process constants, that I will come afterwards. Similarly, chemical equilibrium is the equilibrium of the system with respect to chemical reactions and mass transfers. That means if there is no disequilibrium between the system and the surrounding, by which the chemical reactions or mass transfers do not take place, the system is in chemical equilibrium. That means a system has to be in chemical equilibrium, it should not go for any process involving transfer of masses and the chemical reactions, which causes the species density. You see the multi-component system. So the species amount or the masses of species to change with time. They should not be invariant with time. That means chemical equilibrium is responsible for these changes. That means for chemical equilibrium to be attained, a system and surrounding has to be in equilibrium with respect to certain gradients. What is that gradients? That is the concentration gradients. That is the chemical affinity, the gradients of chemical affinity. These are the things which causes the mass transfer and the chemical reaction to take place. Similarly, again I repeat, for mechanical equilibrium, pressure gradient has to be 0. And the gradients of other quantities which are responsible for other types of work transfer also, that I will come afterwards, should be 0. Similarly, for thermal equilibrium, temperature gradient has to be 0 between the system and the surrounding. So if all these things are met at a time, then the system attains both simultaneously thermal equilibrium, mechanical equilibrium and chemical equilibrium, and as a whole the system attains thermodynamic equilibrium. This is the basic concept of thermodynamic equilibrium. Now after this I go to the concept of thermodynamic process, which is very important. Now thermodynamic process, okay. Now see, what is a process? Very simple, that when a system interacts with surrounding, first of all define a system at an equilibrium state. When a system interacts with the surrounding, a process takes place. How does it interact with the surrounding? In terms of energy transfer. Also mass transfer may take place if the system is not a closed one. Then after some time it comes to another equilibrium state. So from one equilibrium state to other equilibrium state, system comes through a natural process interacting with the surroundings. Now question is very important in this regard. Process is very simple, everybody knows. How to specify the process in thermodynamic coordinate diagram. That means, for example, you see that if I express a system by two coordinates, y and x, let pressure, volume, these are the two primitive variables, pressure and volume here. Let this be the state 1, initial state, and system is allowed to interact with the surrounding in forms of mass, energy, whatever may be, very general open system. And after some time system comes again to an equilibrium condition. Obviously, if you give infinite time, the system will always come to an equilibrium condition when the properties will be same as that of the surrounding, it will come to a dead state. but sometimes we forcefully stop this process so that we forcefully make this system at another final equilibrium state. Let this is 2. So we can tell the system has changed from state 1 to state 2 by a process, but to specify that process in the thermodynamic coordinate by a continuous line, then what we will have to do, we will have to define the intermediate states, the succession of intermediate states through which the system has passed, so that we can define the process as a continuous line on a thermodynamic coordinate diagram. How to do it? Because if we tell that this is one of the intermediate points, this is one of the intermediate points, that means these points we can show only and only if this system is in equilibrium at that state. But when a system, natural process occurs from one state to other state, system is in dynamic equilibrium, system is not in thermodynamic equilibrium. So all the processes are non-equilibrium in nature, means the properties are varying with time, and also properties may not be uniform within the system. So therefore, a natural process can never be shown by such a specified path. To understand it, let us go to this. Let us see that a arrangement like this. Let us consider this. Okay? Any difficulty you now ask me. Okay? This is very important concept. Let us consider a cylinder, a practical case, and a piston. Okay? So many things, and a piston, and a piston. And let us consider the piston is loaded with some weights which are divided. You have read all those things earlier. Any confusion is there, you please ask me. Sir, this is my confusion. Number of weights. And let us consider that there is some gas within the piston, within the cylinder, I am sorry, some gas, and consider this gas as a system. Now this gas exerts some pressure, and at the initial state let us consider the weight and the weight of the piston along with the external weights balance this pressure P. Let this pressure is P1 and initial volume is V1. The system is at state 1. Now let us consider there are 2 stops which allows the piston not to go beyond this. Now what happens? Now this is a system at equilibrium state which is specified by its pressure P1 and volume V1. How it is in equilibrium? Now this pressure P1 exerted on the piston balances this piston weight and the external weights. Okay, P1 into A, the pressure force. So that this is in equilibrium, the gas has a fixed volume, fixed pressure, and along with that other properties are fixed. If it is a system where 2 properties are required to fix its states. All right. Now practically, if we now release all the weights simultaneously, or a considerable portion of the weight from the top, what will happen? There will be a pressure imbalance between the gas and the surrounding. So piston will move upward. Piston will move upward and it will hit the stop, and ultimately it will come here. That means if we finally make this, just remove this, what will happen? The piston will come here. Piston will come here, and at that time an equilibrium state will be achieved with the gases inside, and let this gas pressure will be P2. And in that case what will happen? This pressure will balance the piston weight and the reaction of the stop. Practically what will happen? There will be some oscillations here and ultimately it will be fitted like this. So the reaction and the weight will be balanced by this P2, and let the volume is V2. So the state will be, final state will be P2 V2. So we know the initial state and final state. Now while going so very fast the piston will move. Any intermediate state, if you want to observe by any instrument measuring pressure, temperature, other things, you will see they are not only varying with time, they may not be uniform also throughout. So it is a very fast process, because we want to make it very fast. Obviously we keep a force balance, imbalance in the pressure, high imbalance in the pressure, remove all the weights, then it will come to me. And practically all natural processes are like that. But instead, if we conceive a process like this, which is infinitely slow, like this, instead of releasing the weight one by one, if we do like this, we release the weight like this. If we release the weight like this, that means instead of doing this, if I take a small weight out, that means we create a very small amount of pressure imbalance. So that in that case the piston will move very slowly and come to a equilibrium position like this. That means there is weight. We remove only this one. Stop is there as usual. Stop is there as usual. So this gas is there, and this pressure, let it is P1 dash, which is equal to P1 minus dP. Pressure is reduced by this, and V1 dash, which is equal to V1 plus dV. So piston has moved a small distance, infinite small distance, because the imbalance is very small. And in this way we remove the weights. Let us consider another picture that we have removed another weight slowly. If we think in terms of infinite resolution of the weights and go on reducing the weights like this, and piston will be ultimately coming to this position slowly, and in that case next third position is that this is P1 double dash, it is P1 dash minus dP. Similarly V1 double dash is V1 dash plus dP. So slowly and gradually, if we remove the weight in such a way that all the time we restrict the piston to move infinite small distance under a infinite small imbalance of the pressure. You understand, slowly piston moves, comes from an initial pressure P1 and volume V1 to an intermediate pressure which is slightly less than P1, volume is slightly more than V, and then again slowly if we remove, and if we do like that after a long time, if you do it with infinite resolution of this weight, the piston will come here. And if we do this, then what are the differences? Then all the intermediate state points are almost equilibrium. That means they are equilibrium in the limit. They are in thermodynamic equilibrium, in the limit of thermodynamic equilibrium. To conceive it in an ideal case to be exact thermodynamic equilibrium, you have to stop the process. That means just like consider the walking of an old man. He walks certain distance, small distance, then he stops. Again walk, stops. A small man with a heart disease walks. This is a very good example. He stops, walks, and so then all. That means he covers the distance in such a way that infinite small distance he travels, and then he comes to an equilibrium state. Everything within this system, within his system becomes uniform and invariant with that. But even if you do not stop, if you do it gradually, continuously and gradually removing this weight, then in all the succession states you can think of a sort of equilibrium in the limit equilibrium process. In this case what happened, that if you now PV, that this is your state 1 P1 V1, then all these states if you come like this, you can specify by process, and let this is your P2 V2, and all these succession states you can specify, and you can join this as a single curve, and you can specify the process. That means this is the thermodynamic process. This is the process. So the process can be specified provided the intermediate states, succession states are in equilibrium. This type of process is known as quasi, means almost, quasi equilibrium or quasi-static process. I will discuss at length this thing, reversibles. At the present moment, you just write it that it is known as a reversible process. The concept of reversible process will come afterwards. So one of the criteria for reversible process is the quasi-equilibrium process. This process is quasi-equilibrium or quasi-static. That is almost static process. That means process is almost static. Infinite small departure, then again rest. Infinite small departure, rest. But even if it is done continuously, this gap, this means this continuous, there is the infinite one. Infinite number of small elemental processes we conceive. So that system departs from one state and goes to the other state only under an infinite small imbalance of the properties between the system and the surrounding. So this way this system moves. So in this case what will happen, infinite long time will be required for a system to come from one equilibrium state to other equilibrium state. This way only we can specify a process. So very important thing at this moment you must know that whenever you specify a system, a thermodynamic process performed by a system in thermodynamic coordinate diagram, we always consider the system, the process is a quasi-equilibrium or quasi-static or a reversible process. Okay, now next I will go quickly, time is short for this today's class, which I have thought that I will complete this thing. Now the thermodynamic concept of energy transfer. Okay, let me write thermodynamic concept of energy transfer. Thermodynamic concept of energy transfer. It is very important, thermodynamic concept of energy transfer. Now thermodynamic concept of energy transfer. Now in thermodynamics, the concept of energy transfer, no, thermodynamic concept of energy rather, you cut transfer, thermodynamics concept of energy. Now in thermodynamics, energy has been given two status that I will tell you in first law. One is the energy as a state variable, property of a system, energy as a point function, another is energy as a path function. Two forms of energy. One is energy in storage, that a system can store energy. For an example, let us see that a mass of gas at high temperature, what do you tell that gas is storing? The gas as a system storing what type of energy? Because of its temperature, internal energy. Internal energy stored in the gas. You consider a fuel, sometimes we tell the chemical energy of the fuel, which can be converted into heat by burning, then that heat can be converted into mechanical work, but always we tell that chemical energy, that is the bonding energy of the molecules. There are various ways a system can store energy by virtue of its temperature, that internal energy, that is more precise the intermolecular energy, chemical energy. Another thing is that a gas, mass of gas is there, you start the gas, you create the motions of these particles, macroscopic particles. Then you consider the gas as a system. Then you can tell because of the motion of the particles, the system stores some energy, which is the kinetic energy of its particles. Another form of energy is the potential energy. What is the definition of potential energy? That means if you place a system in a conservative force field, because of its position in a conservative force field, the system's energy is stored in the system, because some work is done to place it in a conservative force field, non-dissipative work, that is stored in the system as an energy. Always we tell that, for example, gravitational potential energy. In the gravitational field of Earth, always we have some energy stored within us, because of which we can shift ourselves from one position to other. So these are the energy that you are acquainted with, are the energies which can be stored in a system. So thermodynamics tells this energy all together as an internal energy of a system, that is system which has this energy internal within it, stored energy, and that is a point function or state variables. Another energy comes into picture. These are not stored within a system, these are energy in transfer. That means this cannot be conceived when a system is in equilibrium state. This can be conceived only in the form of transit when there is a process takes place. This type of energies are classified into two groups, work transfer and heat transfer, no other groups. So therefore, now I can write the thermodynamic concept of energy is that one is energy in storage, very important this thing I am telling, one is energy in storage, which is known as internal energy in general, though we mean by internal energy colloquially intermolecular energy by virtue of temperature, not that, all form of energy which is stored internally within system. So this is a point function, because I know that internal energy is a property, state variable. That means this is associated with the state of the system. Another form of energy is energy in transit, which is the energy which is transferred between a system and the surrounding. So these are path functions, this is path function. And this energy in transit or energy transfer again can be divided into two groups. One is work transfer, another is heat transfer. So I have given the examples of energy in storage, internal energy of a system, point function and state variables. Energy in transit, which only comes into play when two systems interacting with each other or systems surrounding interacting with each other. One form of this energy in transit is heat, that is the energy in transit by virtue of a temperature difference and flows in the direction of the negative temperature gradient, means high temperature to low temperature. And all other form of energy transfers are all work transfer. Usually mechanical engineers will be little biased to tell work means mechanical work, it is F dot ds. No. All other form of energy transfer, it may be an electrical energy transfer. If you put a voltage across a resistor which allows the current to flow, then electrical energy is being transferred to the resistor as a system, that is work transfer. But we use an adjective to separate it from different categories of work transfer. That means another adjective is used, mechanical work transfer, electrical work transfer, magnetic work transfer, you understand. But all are coming under the category of work transfer. Only heat is the different category of transfer which takes place by virtue of the temperature difference. So these are the two different forms of energy, the concept of energy in thermodynamics. One is the energy in storage, another is the energy in transit as a path function. Okay. Now we see that there are different form of, time is up, what is the time? 5 minutes left. So I think today we are late. I will stop here today. Just I will ask you that if you have any queries, you can ask questions only, because I will always give 5 minutes time for questions. I will be happy to answer your questions from whatever I have taught today. Of course, a very less amount of things have been told today. Please.
So please explain why natural process can never be specified by paths.
Okay, that is a very simple thing. Why natural processes cannot be specified by path? Because to specify a path of the process in thermodynamic coordinate, how can you specify a path or specify a continuous curve? If you have got intermediate points, you understand? Because to specify a path, how do you draw a curve? Very simple thing. Go back to school level, class 5, 6 level geometry. That to draw a curve, you have to know the number of points. You do not know the equations beforehand. So number of points have to be joined. That means the number of state points have to be known. So whenever a state point is specified in thermodynamic coordinate, the thermodynamic system has to be in equilibrium. How do you specify the system pressure or system? For example, any two properties, x and y. X and y. If you have to show an intermediate points with x and y for the thermodynamic system, for any natural process in any intermediate state, these x and y are not constant within the system. So you cannot specify. At the beginning I told that if you tell, okay, my intermediate points is having this pressure and this volume. But unfortunately, if you measure continuously the pressure and volume, for an example, in a natural process where a gas expands, you will see even the pressure equilibrium is not there internally within the gas. How can you specify the gas by a single pressure or a single temperature? Moreover, they are invariant with them, because the two things are clubbed. A non-equilibrium states where the system changes rapidly and continuously with time, there is no equilibrium within the system itself. So it does not attain a uniform value of the pressure. So therefore, to specify any intermediate points to draw the curve, you require that particular criterion of equilibrium that should be uniform within the system and momentarily invariant with time. So that's why it is all processes are natural processes cannot be specified by a path. Only it can be done if the process is quasi-equilibrium. Any other question, please? Any queries, any confusion? No more questions? Okay, thank you.